Okay, so we've started looking at covalent molecules, where we put atoms together and get them to bond to each other, not through a give and take of electrons and the resulting charge, but instead getting them to share their valence electrons. So covalent is like co-owning those valence electrons. Okay, now because we're doing a sharing of electrons, we can end up with a lot of different possibilities for atoms of the same elements to bond with each other. So for instance, if I try and put calcium and chlorine together, calcium is going to lose 2 valence electrons, each chlorine is going to lose 1. So really the only way I can put those elements together to make a stable ionic compound is to make CaCl2. Okay? 2 atoms of chlorine, 1 atom of calcium come together to make calcium chloride. But if I put together nitrogen and oxygen, since there's not a give and take of electrons and it's sharing, I could make NO2, or I could make N2O, or I could make NO. So there are a couple different versions that I could make that are all valid covalent molecules using the same elements. This makes it kind of hard to predict what a covalent molecule is going to be and what compounds we can make. We also get into some trouble with what a molecule is actually shaped like, since the structure of a molecule can actually determine a lot about what properties it has, what it can do for us, and it's hard to imagine in three-dimensional space how those atoms will arrange to each other. Now in the future we'll be looking at ways that we can predict what the shape of a molecule is going to be, but for now I think it would be good to get some practice drawing out some Lewis structures, so flat diagrams either on your screen or on a paper that show lines for a pair of electrons being shared, and we use the symbols for atoms to show where those are at, and also to kind of get an idea of what that really looks like and means for a physical model of the molecule and a digital model of the molecule. So we're going to be using a website called Molview, MOLVIEW.org, to visualize these molecules, and we're going to be building some physical models that look just like the three-dimensional pictures. We'll also be able to draw what the kind of flat picture looks like on your lab. So that way we can make the 3D model for ourselves and draw the flat Lewis structure like we've been kind of practicing with lines and elements, dots, and things. Okay, so the first two examples we're going to look at are compounds that are commonly found in cleaning agents. The first one is acetic acid. Grab my synonyms here. Okay, so acetic acid is made of 2 carbon atoms, like this, bonded together. One of them is bonded to 3 hydrogens, looks like this. Okay, the other carbon, this is shown in black, hydrogen's white, carbon's black. The other carbon is going to be bonded to an oxygen, which is bonded to a hydrogen. Okay, and so far, we've got this carbon with 1, 2, 3, 4 covalent bonds. It's got an octet. Okay, and this one has 1, 2. So it still needs 2 more bonds to, be stable. Okay, to get that octet. So what we end up with is another oxygen atom that we double bond to this carbon. Okay, like that. So this is our acetic acid, and you might have these kind of rotate around, might be a little bit different in that shape, but for the most part, this is what we've got. We've got 2 carbons here. We've got 1, 2, 3, a total of 4 hydrogens. And we've got 2 oxygens. So you can form a formula using that number of carbons, hydrogens, and oxygens. Now, what else should we kind of consider here? Well, if you've been looking at your polyatomic ions, you might actually recognize something. I'll take this away here. If I lost a hydrogen, this would have a negative charge. 2 carbons, 3 hydrogens, 2 oxygens. This is C2H3O2. Or another way of writing it is CH3COO. This is the acetate polyatomic ion. Okay, so if the name acetic acid has seemed kind of familiar, okay, That's because acetic acid uses the acetate ion, just with a hydrogen added onto it. It's kind of interesting. And this is how we end up naming a lot of acids, a lot of common ones, at least in chemistry. Okay, so your polyatomic ions are actually made of covalent bonds. It's a covalent molecule that just happens to take on a charge as this takes an electron from something or gives an electron to something, or, in some cases, shares electrons to make a covalent bond instead. It's pretty interesting. Okay, let's look at another example. Our other cleaning product example is hydrogen peroxide. So hydrogen peroxide has two oxygen atoms bonded together, and each of those is bonded to a hydrogen. So they each have two covalent bonds, one to oxygen, one to hydrogen. So they get up to their 8 valence electrons. They've got 6 to start out with, get a 7th from the oxygen, get an 8th from the hydrogen. Good to go. And the hydrogens are okay with having just 2 valence electrons, the one that we start with and one that they share with the oxygen. Okay, so this is hydrogen peroxide. Again, it can rotate to be in a couple different configurations, but this is essentially what it wants to be like. So you could use this formula to figure out a name for this compound, okay, based on the number of H's and O's that we have on here. Typically, for hydrogen peroxide, we put the H's first, okay, so it would be like H2O2, and then you can form the name off of that. Okay, let's look at another set. These next molecules you can find if you are dealing in welding. One of the common fuel mixtures that we use in welding is acetylene and oxygen. Oxygen is probably a familiar thing for getting stuff to burn very well, and acetylene is another one. Okay, to make acetylene, we need 2 atoms of carbon, okay, and 2 atoms of hydrogen. But if you go and look up the structure for this, for acetylene, it does have 2 carbons and 2 hydrogens, but it doesn't look like this, okay, because our carbons are not satisfied with this. We have each carbon with 4 electrons to start, and then a 5th valence electron coming from the hydrogen and a 6th from the other carbon. So we're still missing 2 electrons. We still need 2 more covalent bonds to make these guys happy. Hydrogen doesn't have any more valence electrons to pitch in, so our best bet is to make a triple bond. 1, 2, 3. There's our triple covalent bond between these 2 carbon atoms. Okay, so we've got 2 carbons, 2 hydrogens. In this case, we like to list the carbons first. So this is acetylene. Okay, and then oxygen, just like the stuff we breathe in the air, okay, is a diatomic molecule. It doesn't just sit around as single oxygen atoms. It doubles up. We can make an oxygen atom happier and get it to an octet if we bond it to itself in a diatomic molecule like this. Pretty simple. All right. So 2 oxygens to make this one. Scooch these out of the way. Next up, in a similar kind of theme, burning things, getting things hot, from the welding and stuff, we're going to look at the gases that you find in natural gas, like the stuff we use for our Bunsen burners, or what you use for a gas grill, or a gas stove, things like that, water heaters. So let's look first at, let's see, what do I want to do first? We'll do propane first, okay? So we've got propane and some propane accessories. Propane is made of 1, 2, 3 carbon atoms that are each full of hydrogens, enough to satisfy the octet rule for all of them. 2 and 3. So what we get is something like this. Okay, so we've got 1, 2, 3 carbon atoms. The end ones have 3 hydrogens each, and the middle one has 2 hydrogens each, since it's already got 2 bonds to these carbons on the sides. So in total, we have 3 carbon atoms and 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms. So this is propane. The other gas that's most common in a natural gas mixture is methane, and it is surprisingly simple. It is just 1 carbon atom with 1, 2, 3, 4 hydrogen atoms bonded to it. Okay, so this is methane. Okay, and again, these carbon atoms really exemplify the strange shapes we get for these molecules. You know, you might draw it out kind of in a cross, like you see H, 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 like that, or in a diamond, H, 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 H. But really, this is three-dimensional. It doesn't just all sit flat next to each other or something like that, which is pretty interesting. Okay, so that's methane. 1 carbon, 4 hydrogens. Next up are some smelly molecules. Okay, now the models don't smell, but the actual chemicals that we're going to model do. The first one we're going to look at is ammonia. Okay, you might know ammonia from like glass cleaners, but it also has a part in a lot of stuff that smells bad. So this is ammonia here. You can find it in sewer gases, that come up from grates and things like that. It is a nitrogen atom and 1, 2, 3 hydrogen atoms. Okay. So our nitrogen gets an octet by making 3 covalent bonds to these 3 hydrogen atoms, and they all have a duet. They all have 2 electrons total from the valence electron of itself and the other nitrogen. Okay, and you'll also notice this is not flat. Okay, they're a little bit offset. Okay, it's not like they're all kind of straight in a line with each other. They're a little kind of bent off of each other. Kind of like there's like room for something else up here. So again, we'll get into why we have this kind of peculiar lumpy shape in the future. Okay, the other smelly molecule we're going to look at is sulfane, which is made of a sulfur atom, which I'm showing in yellow here. Got hydrogen there and hydrogen there, just like that. Okay, so this is sulfane, 2 hydrogens, 1 sulfur. Okay. Okay. Kind of as a tip for our ammonia, this guy right here, we're going to put nitrogen first and then hydrogen. That way it'll come up in mole view a little bit better. Okay, and for sulfane, we're going to put hydrogen first and then sulfur. Okay, but again, also if you type in the name ammonia and sulfane, it should come up pretty easily. We're going to try and figure out the formula and the name for both of those. Okay, if you hear like the rotten egg smell or something like that, usually this guy is what's responsible for it. And a lot of other sulfur-containing compounds have an issue with, that smell. Sulfur as an element, not so much actually, but compounds that come from sulfur definitely usually have a pretty rank smell. All right, let's move on to something else. Okay, next up, let's do isopropyl alcohol. So we're going to look at some common solvents. Solvents are just chemicals that can be used to dissolve other things. Okay, and these also might be a little bit out of order. I'm trying to keep it in order as best I can, but as I'm grabbing models, it's a little off. So just look around and find the one we're talking about, and you can work on it from there. So isopropyl alcohol is made of 1, 2, 3 carbon atoms, kind of like propane was. Okay, it's like isopropyl, propane. There's kind of a similarity in the name there. Okay. We have 1 oxygen atom bonded onto here. Usually you'll see it on the centered carbon atom right here. 1, 2, 3. The outside carbons have 1, 2, 3 hydrogens each. Okay, and to satisfy the octet on this oxygen atom, it needs hydrogen there, and this carbon needs one more bond to a hydrogen there. Okay, so in total we have, let's see if I can position this a little bit better, 3 carbon atoms. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms, and 1 oxygen atom. Okay. I would recommend doing carbon first, and then hydrogen, and then oxygen. Okay. Another popular solvent that we use in chemistry quite a bit is called hexane. Okay. Hexane is made of 1, 2, 3, 4, 5, 6 carbon atoms all strung together. Okay. Hex is a pretty common prefix for 6, so we have 6 carbon atoms here. Okay. Now each one of these carbon atoms is going to be full of hydrogen atoms. So let's make some bonds here, and I'm going to be careful not to drop this because this is going to be quite a bit going on here. Just 2 more. Make sure I don't bust this. Ooh. Make sure I don't break this thing. And last one. Nice. So this is hexane. Okay. So in total, I'm not going to try and move it too much because I don't want it to fall apart. But in total, we have 6 atoms of carbon, and we've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogen atoms to make this guy up. Okay. Best to probably put the C's first, the carbons first, and then the hydrogens after that. Okay. So those are 2 popular things we use in chemistry to dissolve stuff. Okay, if especially water's not working out too well. Let's look at some others. I think these are actually the last 2. Okay. Now, this next one is called octane. It and the other chemical we're going to see last, benzene, are both common anti-knocking agents that are used in gasoline. So that way your engine runs pretty smoothly when you're using that kind of gasoline. It's full of octane and that kind of stuff. Octane, like hexane, is a big molecule. So I already have this one built, and I'm just going to try and kind of lift it so you can see it. And hopefully it doesn't fall apart on me. There it is. Bad idea. Okay, so let me twist it there. So oct is a popular prefix for 8. So you might be able to guess there are 8 carbon atoms here. And then to go with it, there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogen atoms in here. Okay? And you're going to have to trust me on that because I don't want to move this around so much that this thing just like collapses on me. So, there you go. There's octane. So if you ever hear about your gasoline having like a high octane rating, that's the molecule they're talking about. Okay, and the last one, benzene, looks a little bit different because the atoms that I have been using don't work too well with doing this structure. It's kind of lopsided and it doesn't give you a great picture of what it's supposed to look like. So instead, we've got this guy right here. Okay, so benzene is a ring of 6 carbon atoms. You'll see there, 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 and there. Okay, they have alternating double bonds. So we have a double bond, and then a single bond, and then a double bond, and then a single bond, and then a double bond. Okay, and these points out on the ends would be hydrogen atoms. Okay, so we have carbon, 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 and then hydrogen, 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 hydrogen on the outsides there. Okay, so this is another thing you'll commonly find in gasoline called benzene. Okay, and the structure you'll see on MolView is a lot cooler, I think, than this one is, but this gets the point across. This one's nice and flat, which makes it a very interesting molecule compared to the others, which have been, very bumpy and bent and all kinds of different shapes. Okay, so the rest you can figure out with MolView by seeing a 3D shape of the molecule you can spin around, and it'll also generate for you a Lewis structure that is pretty close to what we have been drawing in class. They just leave out some extra valence electrons that we'd normally put on there just to keep it a little bit cleaner and simpler.